So that like we are going to use that for programming to be continuously on it. So of course we are going to do maintenance of that, but not over just over the time, not immediately. So yeah, I know what it's very
Go ahead.
for instance.
Oh, I have to mention.
Why because you are not
Yeah. Very different.
yeah, sure.
Research. Oh, yeah, just doing that way. Okay. All right, I'm Stan Moore from San Diego National Labs, and I'm going to be talking about Kokkos, just give a basic introduction. And then the next session will be more focused on LAMMPS. So this is by no means an exhaustive introduction to Kokkos, but it's more focused on what's applicable to what would be necessary for programming in LAMMPS. Okay, so just a brief introduction. I'm one of the co-developers at San Diego National Labs in Albuquerque, New Mexico. Been at San Diego for about 12 years. I'm the main developer of the Kokkos package in LAMMPS. And then I've also worked on long-range electrostatics, have a PhD in chemical engineering, and my dissertation was on predicting chemical potentials. Okay, so just here's some motivation. Currently 9 out of the top 10 supercomputers use GPUs. If you've been following, this has steadily grown from 0 to a few to almost exclusive. And all 3 of the exascale machines will have GPUs. So Frontier and Aurora have broken the exascale or exaflop barrier. And then the El Capitan is going to come online soon. So to run these accelerators, you really need special code beyond just the regular C++ and MPI and LAMMPS. So you really need these vendor libraries or programming languages. So here's just a simple diagram. So say you want to run on NVIDIA GPUs, you want to run on AMD, Intel GPUs, as well as CPUs. Well, if you want to get the best performance, you really should be using the vendor supported or provided libraries like CUDA, HIP, SYCL, and you can also use OpenMP. And in order to do that, worst case, we'd have to have many versions of LAMMPS. We'd have to, take the time to port LAMMPS to CUDA, to HIP, to SYCL, to OpenMP, and maintain all of these versions, which with limited developer time isn't really feasible. And so Kokkos comes in as really an abstraction layer between the programmer and all these GPUs and accelerators. It allows the same C++ code to run on multiple hardware. And so the idea is that you just write your code once in Kokkos, and then you let Kokkos map it onto backend languages. If some new machine comes along, you add a new backend into Kokkos. You don't have to change the LAMMPS, except maybe some trivial changes. So how does it work? Kokkos is really 2 main parts. First is parallel dispatch. This is taking, a kernel and mapping it onto different backend languages like CUDA. And then there's also Kokkos views. So these are multi-dimensional arrays that you can change the layout and different properties. You can optimize for certain hardware at compile time. This is used on top of MPI and LAMMPS, and Kokkos is open source. It's used in many different projects, not just LAMMPS. So you can learn more about Kokkos on their wiki. Okay, so if we take that previous example, we want to run on all these different hardware. Now we're going to write LAMMPS once in Kokkos, And then Kokkos is going to map to CUDA or to HIP or to SYCL or to OpenMP. So this is a portable solution, and ideally we want performance portability, which means that we'll get, reasonable performance and be portable. Okay, so we talked about these two parts of Kokkos, parallel dispatch. So there's a few different flavors. Parallel 4 is just a simple run a loop in parallel. Parallel reduce is the same run loop in parallel, but you're also going to compute one or more global reductions. So that could be like the global energy, or you need to sum those velocities to get temperature. And then there's also a parallel scan. So parallel scan is a prefix reduction across threads. We use it a few places in LAMMPS, but it's really not that common. But it's very useful. There's also more complex hierarchical or nested parallelism with teams, as well as the ND range policy. But again, these are used rarely in LAMPS. And so really, the basic parallel 4, parallel reduce are what we use, kind of the bread and butter for LAMPS Kokkos. Okay. And so just diving a little bit more, we really need to encapsulate one iteration of the loop body. So in LAMPS, we typically thread over atoms. And so we need to somehow get this loop body and pass it into Kokkos. So there's 3 different methods that we use in LAMPS. There's a functor, there's a tag kernel where you pass the whole class into Kokkos as the functor, and there are C++ lambdas, which are anonymous functors. So functors are the most general, but they also take the most programming effort. So you have to copy all of the data, all of the views into the functor. And so in LAMPS, we typically use tag kernels for convenience. I'll give an example of this later on. We can also use C++ lambdas for simple kernels. So that would be like a Kokkos lambda, but there are some gotchas that you need to pay attention to with lambdas. So if you try to capture the this pointer either explicitly or implicitly, then you need to use Kokkos class lambda, which has some further requirements that you can look at in this lambda user's guide. It can also give some bogus warnings with NVIDIA GPUs, so just something to be aware of. So typically I use lambdas for simple kernels. If it's really complex, then I'll use a tag, or in some cases we have to use a functor. Okay, so in order to make this a little bit more concrete, we're going to look at some examples of code. So this is just the regular Kokkos repository. So github.com, Kokkos, kokkos.git. I've already cloned it, but these are the steps that you need to. So my hope is that I can share some examples, and then after you can look at it on yourself and go through it and run them. So I'm going to run them, but if you have any questions, please feel free to ask me live. Something doesn't make sense. For demonstration purposes, I'm going to be using the threads backend. So this is just like a POSIX threads for my Mac laptop. So I have 4 cores, so I'll use it for 4 threads. For Kokkos, you do need a C++70 compiler, which is pretty easy nowadays. Just can't be a super ancient compiler. The Kokkos example tutorial uses a makefile, and so I just built it, and then I'm going to run it, and I can set the number of threads with this command like argument Kokkos num threads. And one thing to notice is that when we run this, the loop iterations execute in random order. This is really important. So Kokkos does not guarantee an order of how the loops are executed, or the iterations in a loop. And so if your algorithm depends on that, then you're going to have a bug. Okay. All right, so I'm gonna go to example, tutorial, and I'm gonna go to the hello world. I've already built this, so we're gonna look at the source code. And these tutorials are nice because they have comments that kind of explain what's going on. And so you can look through the comments, and so I'm gonna go up to the top here. We just have the Kokkos license, some include files. One thing that I'll point out is that, so here's the main function, and you need to initialize Kokkos. So anytime you use Kokkos, it has to be initialized. That's already done in LAMMPS, but just something to be aware of. It's going to print out which execution space. We'll talk about that more in a little bit, but it's the threads. So that's basically the backend threads. So it's just a very simple hello world. This is what it would look like in OpenMP, if you're familiar with that. So it's just a loop from 0 to 15 and with a printf statement, and you're just printing out hello from, and then the iteration of the loop. So here's the Kokkos code. You have Kokkos parallel 4. This is just a label that can be used in profiling tools. This is the number of like the loop bounds 0 to 15. And then this is the functor hello world. And so if we go up to look at the functor, you can see there's a lot of comments that talks about it, but it's pretty simple. This Kokkos inline function just says the function is inline, but it also adds some decorators if you're on a GPU to say that it's a host device function. And so this will allow you to either run on the GPU or the CPU if you're using a GPU backend. You have this operator, parentheses operator, so that's how Kokkos works, the abstraction. And you can see that this is just one iteration, the ith iteration of the loop. And then you have this printf. We use Kokkos printf because it's portable. All of the backends support printf. And then same code as the C++ version. And then so we run this parallel 4, and then we call Kokkos finalized, and that's a hello world example. So if we run this, okay, so if we run this, you can see that it does indeed give a random order. I'm running with 4 threads. If we just run with 1 thread, then it is a deterministic order because it's just serial. But again, I can't stress it enough. Kokkos assumes a random order, and so you just have to make sure that your algorithm can support that it doesn't matter which order the loop is launched in. Okay, so that was just a functor. Now let's look at the Lambda version. So it's very similar, but instead of having that functor, we just have the main function. We initialize Kokkos, and then we print out the default execution space. And then here is the lambda. So you can see that the lambda is inside the parallel 4. So we're doing 15 iterations, and then we have this lambda. We put in the printf in the lambda, and then, so the lambda is nice. It's a lot cleaner. It's a lot simpler, but again, there's a few gotchas you just need to be aware of. This pound if defined is not needed. It's really old, outdated. So don't worry about this pound defined. You definitely don't need that. It's for like CUDA 7, and we're on CUDA 12 now. So these are a little bit old. So if we run this, you can see that we get exactly the same output. So So it doesn't matter if you use a lambda or a functor, functionally it's the same. Okay, so we already went through the hello world lambda. Okay, now we're gonna look at a parallel reduce. So that was just a simple parallel 4. Now we're gonna compute the sum of squares of integers from 0 to n. In the simple reduce, so again, it's just similar. We set the number of threads. I'm gonna go to that. Okay, so here's our functor, square sum. And again, this is a parallel reduce, so we set the value type. This is the reduction type of integer. So we're going to be summing over integers. Here is the operator. So this is our sum. We're just doing I times I and then adding the result, and then that will get computed as the reduction. So again, this is just one iteration of the loop for I. Here's the main function. Here's where we launch the parallel reduce. So we have, here's our global reduction variable sum to integer. And then this is the number of iterations. So we're doing 10 iterations. We put in the functor, and then we also put in the reduction variable as well after the functor. So we run that, and then this is just a printout of what it got, and then we also compare to a sequential loop. So this is the exact same loop, just serially. So here's the sum variable. We just loop over 0 to n, and then we do I times I and add it. So this is what Kokkos is doing, and then we just check and make sure that the two computed values are the same. So if we run this, you can see that, so we're going from 0 to 9, so that's 10 values. Computed in parallel is 285, computed sequentially is 285. Everything is the same. Okay, so let's look at the lambda version. So you can see that similar, we initialize Kokkos, but in this case, we don't have that functor, we just have a lambda inside the parallel reduce. And so it's just this code right here, LSUM, and then we put in the reduction variable here, and it also comes in here. And then same code as before, we compute it in this serial. And then I wanted to show one more. It's the tag version. And we use this a lot in LAMMPS. So if you think about LAMMPS, we have these classes like pair style. And so my class is similar. You can think of that as like some pair style. We have a struct, which is a tag. So this is just like an empty struct. And then when we do the operator, so this operator is inside the class, we pass in the tag. This is a parallel reduce again, and then we just have that same I times I. And then what this tag allows you to do is if you have more than one operator in the same class, you can choose which one to launch using the tag. And then this is just a function in the class to execute, do the parallel reduce. So again, we put in, so with the tag, we have to put in a range policy from 0 to n, which is a little bit more verbose. And then the key here is that we're able to pass in the entire class by taking star this, and then we don't have to write a functor. we don't have to copy all the data into the functor. So it's a lot more convenient to just pass in the entire class. So but again, this would be like passing in the entire peristyle, and everything that's in that peristyle is now accessible on the GPU, assuming that you're using Kokkos views.
So this, I think, is the case when we are writing our own Adam stuff and everything.
Yeah.
Probably will be using a couple different functions in the operator, right? And I mean in the sorry,
Yeah.
We have to use the tags basically.
Yeah,
That's
you
what
have to use a
sounds
tag or a lambda or a functor. You know, if you have a functor, then it's its own self-contained struct, and you can do whatever you want. Yeah, but if you're using if you want to just pass in the entire class, then you have to use tags, because if you have more than one operator, then you have to specify which one it is.
I mean, for a pair star, usually you would only want to accelerate the compute function.
Yeah. Okay, and then we do the same thing. We just initialize this class after we initialize Kokkos, and then we execute it, and then we compare it to a sequential loop and just make sure that's the same.
Sorry, so in this example, I realize it's still the simple one, but I don't see where you're using it, how you would use anything that's in that tag data structure.
So that is here in the operator. So this parentheses operator, it gets overloaded, and it gets called when you do this parallel reduce here.
But you're saying instead of the simple line L sum plus equal I squared, you could have more complicated code there that accesses things in the tag square sum.
Yeah, because you passed in star this here, and that's the entire class. So anything on the in stack memory, like a integer, like just a scalar, would be accessible from stack memory, because you have a copy of the entire class on the GPU. So this is the functor. So whatever this is gets copied up to the GPU. So previously it was just that little struct of the functor or the lambda, but in this case it's the whole class.
So after this, you can use everything but pointers.
Yeah. So we'll talk more about memory spaces and pointers, but pointers are problematic because they're pointing to CPU memory, which isn't normally accessible in GPU memory, and then you'll sigfall. So that's why we need Kokkos views.
So if you wanted this one function to do 3 different things within the peristyle, you would set some class variable in tag square sum. And then all the threads would check it and say, if it's equal to 1, then we're going to do this operation. If it's 2, we're going to do something else.
Yeah.
Okay. So you don't have different threads do different things, but you have all the threads read the same settings from tag square sum.
Yes.
Okay.
I have another question kind of over in the same kind of space. So I have some experience with CUDA. And I remember that basically that LSIM plus equals I times I, it was very easy to do that wrong and get wrong sums, kind of like when you do that check for the serialization. It seems like Kokkos handles that all for you, right? Okay.
Yeah, so Kokkos is nice with the different backends that will do like a shuffle or whatever it needs to do under the hood.
Right.
Yeah. So it's basically guaranteed to get the right result.
Sorry, I don't understand how you can get that wrong. How can CUDA get it wrong?
If you're like using low level CUDA, then you have to do like shuffle operations and fairly complex.
Well, you basically have a race condition accessing LSUM.
Right. Yeah.
Oh, but I thought that's what the reduce is supposed to automatically.
Yeah, it
take care
does.
of.
It
Oh,
does.
but you're saying that's really a Kokkos.
Yeah.
Right. Yeah. CUDA, it's very easy to do that wrong.
Okay, thanks for pointing that out.
Okay. So just for illustration purposes, we're going to take a simple reduce. We're going to tweak it a little bit. So we're going to we're gonna time this and see what our parallel efficiency is. So we wanna do more iterations, so it takes longer. I'm gonna do, sum of square root, so we don't overflow. I'm also gonna change this reduction type to a double instead of an integer. So this
Not
has
overflow, it's him.
double, and then we have to print out a double as well. And then the reduction variable has to be a double. Okay, and then I want to do a square root here. Okay, so this is just, I'm going to do a billion iterations just so that it takes a while. Oh, and
Did you want to do just square root of I, not square root of I squared?
yes, that's a good one. Let's see. We'll just do I, and then we'll also, I'm gonna get rid of this sequential loop because that will take forever. And I'm just gonna return one here. Okay, so we're gonna just run it in serial. Takes a while, about 3 seconds. Oh, we have a segmentation fault. Let's see what.
You have to make I a double too? The operator?
So actually, I have the right answer. Oh, I whacked Kokkos finalized. Okay, we're gonna remake it. And rerun it. Okay, so it's some huge number, taking the square root, the sum of the square root of integers from 0 to almost a billion. You can see that it took about almost 3 seconds here, 2.789. So if we run it with 4 threads, you can see that it's 0.73. If we run it with 2 threads, it's 1.3. So you know, it's reasonable parallel efficiency. We could compute here.
That's after 2 threads is actually more than twice as fast.
Oh, really? So it's 3.8. So not quite 4. So you know, decent. It's you know, this is an embarrassingly parallel. Well, almost because you have the reduction, but it's really huge loop. It's really big, so it's you know it's fairly expected we'll get good parallel efficiency. But just kind of to show you that it is indeed parallel if we run multiple threads. Okay. All right. So that was parallel dispatch. Now we're going to talk about Kokkos views. So you can think of Kokkos views as sort of like smart multidimensional arrays that can be optimized for specific hardware. The views store some metadata, so they store the length of each dimension. Managed views are also reference counted, which is like a smart pointer. So you don't have to worry about memory leaks with views. When the last view goes out of scope, or the last copy of the view goes out of scope, then it's automatically free. We're going to talk about layout. So typically CPUs want a layout right, which is like a row major.
Stan,
Yeah.
there's a question back to the parallelization. Is there a way to enforce the order of the loop?
No, there's no way to enforce the order of the loop. That's just a fundamental restriction of Kokkos. You cannot assume an order.
Okay, thank you.
Okay, so row major versus column major, it's really just which is the fastest index. At, as, you know, how is your view laid out in memory? And so CPUs typically want layout right, which is a row major. This helps cache access and data locality. GPUs typically want layout left or a column major for memory coalescing. But that's not a hard and fast rule. The optimal layout can change if you're using hierarchical nested parallelism instead of flat parallelism. So all the examples previously were all flat, but you can also have, you know, parallelism inside parallelism with different levels. And so just know that you need to pay attention to the layout. The default for CPUs is right. The default for GPUs is left, but experimenting with that can give speed up in some cases. Okay, so now we're going to run a simple view example. So similar to before, I've already built this. And one thing to note is that you must allocate views outside the parallel region. So you can't like create or resize a view inside a parallel for or a parallel reduce. That has to be done before or after the parallel region. Okay, so here is the simple view example. And again, the comments here are useful to go through. It talks and explains a lot. So in this case, you know, a view can be, I think, up to 7 dimensions. But here is just the 2D view. We have one runtime dimension and one compile time dimension. And it's a 2D array of doubles, but the first dimension can be anything, and the second dimension is 3. So you can think of this as sort of like positions and lamps or forces. And so we have a functor here that's just going to set the initial values of the view. So it takes in a view, and then here's the operator, and it's just setting the second dimension, the 3 values to some, you know, the first is I, the second is I squared, and the third is I cubed. And then we have another functor. So this is a second functor that will actually take the values of the views and do some work with them.
I like that it says access it like a Fortran array and then it uses 0, 1, 2.
Yeah. I think they mean the parentheses. Yeah. So with the view, if you have a 1D view, you can use the square bracket operator or the parentheses operator. If you have a 2D or more, then you have to use the parentheses operator with commas instead of using the square brackets like in C++. And so here, this functor is just doing another reduction using the 3 you know, values for I and just some kind of random work here. So those are the 2 functors. Now we have the main argument. We initialize Kokkos. We're going to do 10 iterations. Here's where we initialize the view. You can give it a label, so that's like useful for debugging tools. And then you give it the size, and the size is 10. And again, because it's a 2D view, but the second dimension is compile time, then we just give it 1 value at runtime. And then we call a parallel for, which initializes the values. So again, I was just setting them to these I squared, I cubed. And then we call another functor, or another parallel reduce, to actually do the work. So we do a reduction on that, we get back the sum, and then we print out, and then we Kokkos finalize. So
Sorry, what was the reduce operator?
The reduce was doing,
Oh, yeah.
yeah, just this sum over the 3 indices in the second dimension. Okay, so if you run this, gives us the result of the sum. Yeah, and so if we wanted to actually like profile it, then we should do more iterations. I'm just going to do 3e to the 8 iterations. We're going to look at it. Oops. It just takes a few seconds to run. Hopefully. Okay, and there's the result. You can see it took 14 seconds. That was in serial. Now if you run it in parallel, it should take hopefully less time. Yep. So 14 seconds on one thread, almost 6 seconds on 4 threads. So it's not quite as good parallel efficiency. We're doing a lot more memory, with the views. But still, you do get speed up with parallel.
So question, so even though it's a 2D array, your thread index needs to be a single index, which would be like a row of the array?
Yeah. I mean, it doesn't have to be. That's
There's
just
no way to, if there's a big 2D array, you could thread parallel over individual indices or individual locations in the array or something?
You could if you if you flatten the loop. Yeah, or you could use a hierarchical parallel for parallel reduce. Okay, so let's look at the Lambda version. So this one is a lot cleaner. So we have the same view type, and then we initialize the view. And then here is the first parallel for. This is just like before, but we're setting the memory inside the parallel for instead of using a functor. And then here's the second. This is a parallel reduce. We just copied that code in, and then we don't have to mess around with, the functors. And in the functor, we had to copy in the view and all that. So this view just gets captured in the C++ Lambda. Okay, one thing that's nice about Kokkos as well is that you can take a slice of the view. That's called a subview. So you use a standard pair to take a range. So here's an example. We're taking a subview. This is a 1, 2, 3, 4D view. We're taking the subview of A. And then in the first dimension, we're going from 3 to 15 using standard pair. Second dimension, we're only taking the 5th indice. The third dimension, we're taking all, so it's unchanged. And then the fourth dimension, we're only taking the 3rd indice. So again, Kokkos all just keeps the entire dimension unchanged. Standard pair takes a range. It's also really nice to use auto for the return type of the subview because it can be quite complex. It could be a strided layout, and so using auto is really nice. But again, this is only used a few places in LAMMPS. You might see it once in a while, but we don't use it that often. But it is a nice Kokkos feature. Okay, so let's talk a little bit about execution and memory spaces. So when we say host, that means CPU. So this is assuming that we have both CPUs and GPUs. Device means the GPU backend. It could be CUDA or HIP or SYCL. But again, host is the CPU backend. It could be the serial or OpenAB backend or the Threads backend like I'm using for the demonstration purpose. GPUs typically have high bandwidth memory that's not accessible on the CPU. And so if you try to take a pointer, to CPU memory and access it on the GPU, you get a segmentation fault. And same if you try to access GPU memory on the CPU memory. There's also performance penalty if you have to transfer data between the GPU and the CPU. So the rule of thumb is to try to keep memory in the GPU as much as possible to avoid this overhead. There are ways to simulate unified memory in software. So that does page migration, but it can be slower than the method that we use in LAMMPS of just explicitly managing memory ourselves. I will note that, state-of-the-art systems like NVIDIA Grace Hopper and AMD MI300A are an exception. They actually have unified memory and hardware. And so, some of these overheads are not applicable, or at least a lot smaller. Okay, so how do you transfer data? So if you just assign one view to another, that's a shallow copy. That's just like a pointer. There's no memory movement except, you copy some metadata, and you also, if it's a managed view, you increment or decrement the reference count. But the actual data isn't actually copied in a shallow copy.
And this reference count is incremented or decremented on the CPU, right?
It's actually both. So if you have a device view in GPU memory, it actually uses atomics to increment the reference count, because it needs to know when does it go out of scope on the GPU and when does it need to free that view. Okay, so there's a couple different ways you can transfer data. So Kokkos deep copy is sort of like a mem copy, but it can go across memory spaces. So for example, you could transfer data from the host CPU to the GPU, or vice versa. You can also do a deep copy on a view of the same memory space. So if you actually want to, just duplicate this view in another view, but move the memory, then you can use a deep copy as well. You can also use Kokkos create mirror view, which makes a mirror view on the opposite memory space. And so if you want to, if you have data on the GPU and you want to copy it to the CPU, you can create a mirror view on the CPU and then deep copy into that mirror view. Okay.
So can we think of these views as basically like shared pointers?
Basically, yeah. Shared pointers that work on GPUs.
Yeah. Like obviously not just shared pointers because they can't transfer memory. But yeah, it seems to follow this like the same.
It's similar. They do have this metadata where you can query, how big is each dimension.
Okay, so it's like a shared pointer for specifically like a matrix or a sensor.
Sort of, yeah.
All right.
Yeah.
So do you have an example off the top of your head on when we need that in LAMMPS, LAMMPS code, when we have to do a shallow copy?
Yeah. So we'll talk more about that. But a shallow copy is just if you just want another reference to this view to use somewhere else. You can also do a shallow copy from a managed view to an unmanaged view. So unmanaged doesn't have reference counting, because if you really don't want to reference count inside a parallel loop, you can have some overhead. So an unmanaged view gets rid of that overhead. We'll talk more about it. Okay, so now we're going to look at the simple memory space example. Okay, so we have same view type, 2D double, and then we also have this host mirror type. We have a reduce functor, so we're going to do a reduction over the 3 indices. It's a little bit different than before, but just, you're doing this sort of like a matrix operation or something like that. Okay, here's where we initialize the view. And this view is by default in the default execution space of Kokkos, which means that if you're running on a GPU, this would be a view in GPU memory. And so if we want to do something on the host CPU, then we have to create a mirror view using the host view type. And with that mirror view, then we can just do a sequential loop and initialize the values to something, whatever we need. You know, in LAMMPS, this would be like, sometimes we initialize like a spline table in EAM. And, you know, that's hard to do on the GPU. So we just do it once on the CPU. And then we have to copy the data from this host view into this device view. And then we'll use the device view in all of the parallel regions on the GPU. So again, here we created a mirror view. We did some operations on the host CPU to fill it, and then we copied it into GPU memory here. And of course, I'm running on a Mac CPU, so it's not as interesting if we had two different memory spaces. With the CPU backend, like threads, these are all just no-ops, because there's only one memory space, and so it doesn't actually, well, I suppose that this create mirror view will just give like a reference to the same view on the CPU, so it's really a no-op. Then we're going to do this parallel reduce. So again, the functor was here, just this sum over the indices, and then the sum value is always copied to the host, so we don't need to worry about, you know, copying the scalar or which memory space it's on.
I'm slightly confused as like how we know, like I just like looked at this like code. How do I know what memory, what variables live on a device and what live on the host? Like view type A seems to be like default on the device. Is that true of all views?
Yeah, so like it says here, it's in Kokkos's default memory space. There are ways to specify the memory space, but in LAMMPS we have some abstractions that makes it pretty easy to know. But if you just take a Kokkos view here, it's in whatever the default memory space is, and on a GPU that's GPU memory.
Okay.
Yeah, and then to get this host view, you have to explicitly do create mirror view here, which allows you to deep copy.
Right, so I guess the thing to be careful about is that like, if you're working with CPUs, it's fine. But if you're working with GPUs, you just have to remember everything's on a GPU. Mirrors on.
Yeah. Okay, so we'll run this. And just the result is 460 for that, you know, sort of random reduction over indices. And again, you know, if I was on GPU, I could show you, you know, if I went here and tried to access, like if I did a printf of A on the GPU, then I just get a segmentation fault because that memory is not accessible in printf on the CPU. Similarly, if I try to take this host view and I accessed it in the functor here, so if I did HA, which is the host copy, that should also seg fault because it's not accessible. Okay. So another thing to keep in mind is that GPU aware MPI. So normally passing a pointer in GPU memory to CPU is going to give you a seg fault, but if your MPI library is CUDA or GPU aware, you know, it could be HIP or SYCL too. then it actually allows you to pass pointers in GPU memory directly into an MPI call, such as MPI send. This avoids having you to explicitly copy the data to the host CPU first. And then, some machines have hardware support for this, and so it can actually improve performance. Depending on which MPI library you're using, you may have to enable this feature at compile time or runtime. So like on some of the exascale, like Frontier exascale machine, you have to export an environment variable to enable this for create in pitch. With OpenMPI, you have to compile for this, and so if you don't compile, then you'll get the sig fault. LAMMPS tries to disable this feature if it can detect that it's not supported, and it'll give a warning. You can also force it on, so if there's some problem and that your system supports it, you can force it. But if you're getting segmentation faults, then you need to turn it off explicitly and then go and check your MPI implementation. I've got a lot of questions on the form or the GitHub issues. Why am I getting the seg fault? Well, if it runs fine on one MPI rank, but as soon as you do two and it seg faults an MPI call, then it's almost certainly your MPI library doesn't support this GPU-aware MPI. So we talked a little bit about unified virtual memory. Normally we have to manually copy the data, but there are ways using managed memory, which just basically takes care of all this data transfer between GPU and CPU. It's less bug prone, and it's very useful for debugging. So, if you have a bug where you forgot to transfer some data explicitly, then you can turn this UVM feature on, and then it will automatically work, and you can use that to compare and debug. You might be thinking, why don't we always use that? Seems a lot easier. Well, it can be slower than just copying the data manually, because you have to wait for the OS to page fault and migrate pages back and forth. One thing that it does allow you to do, if your system supports it, is you can spill out a GPU memory into a much larger CPU memory. But again, there's performance issues with that, especially if they're spilling a lot. But you can run large systems that don't fit into GPU memory. So you can enable it with force UVM in the make file, or enable CUDA UVM with CMake. I will know that this is a deprecated option and will be replaced with something else in the future, but for now it's really useful for debugging. Okay, so we talked about deep copy, we talked about create mirror view. There's another way to do this in LAMMPS that we use a lot in LAMMPS. That's Kokkos dual view. So Kokkos dual view has two copies of the data, one in the CPU memory and another in the GPU memory. So instead of, it just basically already did that create mirror view, and then it just has it in a struct. It has both copies of the device and host views. And instead of doing deep copy, you use a sync and a modify command to transfer the data. So modify means the data is changed. It's modified. Sync means to copy the data, but only if it was modified on the other memory space. So if you're going to use the data, you need to just call sync. If it hasn't been modified, it's just a no-op. It won't do anything. If it was modified, so if you need the data on the GPU and it's been modified on the CPU, then you call sync, then it will automatically migrate the data to the GPU, make sure that it's up to date, it's in sync. If you try to modify both on the CPU and the GPU without a sync in between, then that's an error. So any questions on that?
So modify means I make some changes and then I use the flag to tell to the view that I modified it in this space.
Yeah.
Yeah. So I have to explicitly say I modified this, the GPU version, I modified the host version.
Yes. And as you can imagine, this is error prone, and if you forget to mark it, then you have a bug, and that's where the UVM can come in handy because it just bypasses all of this sync and modified, and you will automatically get the correct answer. But doing the sync and modify manually is faster in most cases. So just think about.
So you can also pool things, so you do multiple modifications, and then you just flag them as modified when you're done.
Yeah. And if you call modified on the same space twice, it's, you know, it doesn't really do anything. And if you call sync and it hasn't been modified, it doesn't do anything. So it's safe to do this multiple times. And this way, you know, you're only transferring the data when you need it. So if you think about running a peristyle, you know, at the beginning, you probably need to sync the forces and the positions and maybe a few other atom arrays to the GPU. And then you're going to do your force calculation, and then you modify the forces, so you have to mark those as changed, as modified. And then say, you know, you do a thermal output and you have a dump file and it's using those forces, then it will sync those to the host, and then it will transfer the data down to the host, and then it'll dump it out in a dump file. Okay, I want to talk a little bit about thread safety. So this is something to think about when you're writing in parallel. So if you have two threads that are writing to the same memory location at the same time, this causes a data race. You don't know which one's going to win. One's going to stomp on the other and override its value. So this is like what you're talking about with that reduction. If you don't do that right, you don't have thread safety, then you'll get the wrong result. So this happens in LAMMPS when one thread is updating the force on atom I, like with a half neighbor list. Another thread is updating the force on neighbor J, and it's the same atom. So they're both trying to, you know, add to the force or modify the force, and you know which one's going to win. So on GPUs, we protect that with atomic operations, so thread atomics. Kokkos supports both individual atomic operations, so just like a single addition, or you can also mark an entire view as atomic, and then all of the operations on that view will also be thread safe. On CPUs, atomics are generally slow, and you also are using a low thread count, you know, 16 threads or less, typically on CPUs for multi-threading. So in that case, we want to not use atomics, we want to duplicate memory for each thread. So each thread has its, you know, private scratch space that it can do its own work on. And then we take all those copies and we sum them up at the end, which can be faster than using atomics, but also, you know, you have to duplicate your memory. So again, you know, it's not going to scale up to thousands of threads, you know, maybe 16 at max. This is what the OpenMP package does it doesn't use atomics, it uses data duplication. So Kokkos actually provides an abstraction that has both options. It uses atomics for the GPU and data duplication for the CPU in what's called a scatter view. So in LAMMPS, you'll see that sometimes, and it can help performance on the CPU. And again, so you cannot assume a specific order of loop execution, so that's not thread safe. So if you're trying to use the value from one iteration and another iteration, you don't know if that iteration has even run yet. And so that will create a bug.
Question, so the atomics idea that you have this code that is going to have this race condition, does atomics just automatically detect statements where that's happening and when it happens sort of real time and fix, or you have to flag things as here's a potential issue right here?
So if you know, like, if you know that you're going to have this thread safety issue, then you can just mark, or you can just get a Kokkos view that is atomic. Like, all of the operations on that will, like, if you do any additions, it will be atomic. So in LAMMPS with the half neighbor list, we we mark the force view as atomic. And so then just any operations that are summing forces will be thread safe. One thing to keep in mind is that atomics have overhead. The atomics on GPUs are incredibly fast, or at least most GPUs. But there is some overhead, so you don't want to use atomics always. If you're just reading from the forces, then you can just use a regular view. You don't have to mark it as atomic. It's only if you're modifying, and only if two threads can hit the same location at the same time.
So again, as I mentioned, you have to think about it. You have to decide whether or not it might happen, right? So
Yeah.
it's a decision you make.
Decision you make, and yeah, we'll talk more about debugging in a little bit, but if your answer is non-deterministic, then there's a good chance that you have a race condition.
Just from OpenMP threading, sometimes, so typically you try to multi-thread across the outermost loop or flatten the loop. In some cases, to avoid any race conditions, from a multi-level loop, it would be better to multi-thread the second level or the third level. And so you can still have threading, and at that loop level, you're avoiding race conditions. But most of the time, you want to be on the outermost level to have the best, the most efficiency and the lowest overhead.
Yeah, and we'll talk more about this later, but if you use a full neighbor list so that you're duplicating the work for pairwise potential, you don't have this race condition. And so on GPUs, that can be faster because you have a lot of, compute power on the GPU. So it doesn't matter if you're duplicating the work, and you can have less overhead.
Yeah, then you have to watch out for random numbers. So like DPD, where you get a random number for a pair of atoms, that needs to be the same. If you're just using a full neighbor list, then you would get different random numbers, and then your system is no longer balanced, and you just get garbage.
Yep. Okay, so now we're going to look at the simple atomic example. Okay, so here is the example. We have a 1D array of integers. So this is the device view, and this is the host mirror. And we also have this, so this count is just a scalar view here. That's just a single integer. And then we have a functor that's going to find a list of primes in a random set of numbers. So if we run in parallel, the order of the results is not deterministic. That's true on GPUs. I believe on my Mac it is deterministic. But on GPUs, this would be random order. So here's a functor. They have a few views. They're initializing the functor, and then here's where the work is. And so they're just basically trying to figure out if this random number is prime or not. It's like I said, it's not the most efficient prime test, but it works. So they're just doing some math on it to find the factors and to see if it's prime or not. Okay, and then here's where the thread safety issue is. So if it is prime, then they're going to try to insert this into a 1D view and make a list of all the primes that it found. But the problem is that each thread is finding different prime numbers, and they're all trying to insert this into this view. And so we're going to use a Kokkos atomic fetch add on this count to get the location in this 1D array where to put the result, because we want a list of all the prime numbers we found. And so what this atomic does is it gives us the current position in this variable IDX, and then it will increment this count view by 1. And then we can take that index and use that to store the prime number that we found. And so it just guarantees that only one thread will get an index here. And in this way, each thread can get a unique place to put its prime number in the 1D array. So if we took this atomic out, and we just did something like this, then that would be not thread safe. And if we ran it on GPUs, then it would give the wrong answer because, multiple threads would hit this. You might get redundant indices, and then you get, you lose some of your list of prime numbers. It doesn't work on my CPU. I don't think there's enough threads. Only 4 won't hit it at the same time. But on a GPU, I guarantee that this would give the wrong result. Okay, so we're going to run this. And so in 100,000 random numbers, it found almost 10,000 prime numbers. If I run it in serial, it's the same because on a CPU, the random number generator, I believe, is determined. Okay, so one thing that you might wonder is, I'm trying to use Kokkos. How do I know if it's actually running on a GPU? So there's a couple different tools you can use. NVIDIA SMI or Rockin SMI for AMD GPUs. And it will give you, so this is NVIDIA SMI, it gives you a lot of good information. So it will show you the GPU utilization. It will also show you like the driver and CUDA version. That can be helpful with debugging. But if you have more than 0% utilization, then you are likely using the GPUs. This is a single node that has 4 Tesla V100s. Okay, so you have written some Kokkos code and it's not working, or you need to debug it. How do you do that with Kokkos? So one key that I just want to hammer is that it's much, much easier to debug on the CPU than on the GPU. So you want to try to use the CPU as much as possible to fix all the bugs, and then only after you have it working on the CPU, go to the GPU and try to debug that. So the first step is to remove any non-determinism. So in LAMMPS, that's mostly commenting out fixed longevon, which is a thermostat that uses random numbers. And so if you're running on if you're running fixed longevon, that will give non-deterministic results, especially on GPUs. And so if you can comment that out, and maybe use a different type of thermostat, or just use the fixed NVE. The second step is to match the Kokkos serial backend. So looking at like the LAMMPS log file with the vanilla CPU version. This is assuming that you have just a working CPU version already. If you don't, then it's probably a good idea to start with that, because in LAMMPS you'd probably need that anyway to get your code released in LAMMPS. And so how do you match this serial version? Well, some tools are Kokkos Debug. So Kokkos has some options that will turn on bounds checking, which is really useful. So if you step outside of a bound, the bounds of a view, then it will give an error, and then you can go look and see where you stepped outside and what was the value. So that's really useful. You can enable that both in CMake as well as just the regular make. And you can just use regular CPU debugging tools like GDB, file grind, address sanitizer, because Kokkos serial is just really CPU code, CPU C++ code. And when all else fails, throw in some printfs and, just try to, assuming you have this working version of vanilla LAMMPS CPU, then you can just use printfs and look at the values and see where they diverge. You can also compile with less optimization, like -0 that will help with getting accurate backtraces in GDB or Valgrind or address sanitizer. Once you have the serial version working, so this is just one thread, then you can start running with multiple threads using the OpenMP or the threads backend like I showed here. So you can run on 2 or more threads, and then again, compare either with the vanilla CPU or the Kokkos serial version that you have that's now working. There are some tools like Intel Inspector, which can point to thread safety issues. However, there are some false positives in Kokkos. And again, all else fails, use printf. So the typical issues here, if you've already matched the serial backend, could be a data race or other thread safety issues. The atomics issue might not show up on the CPU because you might not have enough threads to hit the same memory at the same time. But if you have some dependency on loop order, this will definitely show up. And then the fourth and last step is to match the GPU backend. So it could be CUDA or HIP or SYCL with the serial backend or vanilla CPU. Should be the same at this point. And some tools you can use are CUDA GDB, which is like GDB, but it supports GPUs. There's also CUDA MIMCheck, which is sort of like Valgrind for GPUs. You can compile with UVM. So if you think that you have a bug with the sync or the modify data transfer, compile with UVM and then check the values and compare and figure out where they diverge, and then also print it. If you compile with Kokkos debug options, bounds checking does work on GPUs. It may have less functionality than on CPUs. If you compile with Kokkos debug, it will add -line info for NVIDIA GPUs. That's useful, but in order to get a true stack trace in GPU code, you have to compile with -G. And that's like a huge hammer that turns off it serializes a lot of things in the loop, but that's really the only way to get a true stack trace and to get the exact line of GPU code where it's failing. It can also make it run really slow. So typical issues, if you've gotten this far, is just like a missing sync or modify for data transfer. So if it runs correctly with UVM, but it runs incorrectly without UVM, then it's almost certainly a data transfer issue. And then there are also thread safety issues like missing atomics. So missing atomics would be like if your answer changes slightly. So assuming you turn off pixel on and you don't have any random numbers, if your answer changes slightly or a lot from run to run, so you just run it once and then run it again and hit that. If those aren't exactly the same, then there's a good chance that you have a race condition and you need atomics. Okay, so let's say that you've debugged your code, it's working, but you want to optimize the performance. How do you do that? Well, for GPUs, you want to saturate the threads. So that could be either increasing the number of atoms that you're running or exposing more parallelism. So on a GPU, you have, order thousands of threads. And so if you only have 10 atoms, then your loop is over 10 atoms, then you're only going to be using like 10 threads, right? And so there's no way that's going to saturate the GPU. You need, on the order of maybe 500,000 or so atoms if you just have flat parallelism to saturate the GPU. You want to use caches efficiently. So that means improving the memory access patterns, the data locality, being mindful of the layout. You want to avoid transferring data as much as possible. So that means porting all the kernels of Kokkos. Another thing you can do is if you have multiple scalar views, And, you know, you're transferring data from this view and then this view and then this view and then this view. You can just make one big view and then take subviews. But when you do the memory transfer, you just do one transfer and that reduces the latency. You can also fuse kernels if possible. That helps launch latency for small systems. You need to avoid allocating memory every time step. So allocating memory is expensive. And so what we do is over allocate views, and then we only grow if the size is exceeded. We typically don't shrink. What you want to avoid is, you know, having a view that you keep exactly the same size as the number of atoms. If that's fluctuating, then you're going to be allocating over and over and over again. And then the last thing is to watch out for Kokkos view initialization overheads. We'll talk more about this a little bit later, but this is on by default, but there's ways to turn it off. Okay, so some tools for profiling performance. The first thing you can do is just look at the timing breakdown in the LAMMPS log file. So that gives, you know, the time spent in your pair, force calculation, communication, the fixes, etc. Kokkos has some tools. These are portable, so they work for any backend that Kokkos supports. My favorite tool is space-time stack, and I'll give an example of that in a little bit. The nice thing about this tool is that it shows both kernel times as well as memory use, and it's also MPI aware. So if you're running on more than one MPI rank, then it will, you know, sum all the results together. You can use NVProf, which is deprecated now. There's also RockProf for AMD GPUs. So this is like the NVIDIA and the AMD tool. There's also replacements for NVProf, the Insight Compute and Systems tools. And then there's also OmniTrace and OmniPerf for AMD GPUs. For Intel GPUs, you can use vTune, or Argonne Lab has a iProf tool. And then for CPU kernels, you know, there's a lot of different packages. You can use HPC Toolkit, Tau, or just the GNU gprof. One thing to note is that if you're running on NVIDIA GPUs, you need to set CUDA launch blocking equals 1 to get an accurate timing breakdown. Otherwise, because we have some overlapping kernels, that will, if you don't set this environment variable, then you'll get times that are, you know, kind of messed up, and times in one category when they should be in a different category. Okay, so we're going to do another example. This is space-time stack profiling tool. So in order to do this, you would clone, instead of Kokkos, it's Kokkos tools repository on GitHub. Then you need to build this tool. It's just a really simple make file. In my case, I've disabled MPI. And then to run any Kokkos tool, you just export this environment variable, Kokkos tools libs, and then point to the path of this library that you built. So we're going to look at this simple view example, and we're going to try to improve performance by removing unnecessary view initialization. We'll talk about that a little bit in a moment. So we're going to go back to simple view. Okay, so I'm going to export. So I've already built the tool space-time stack. I'm going to export that, and we're going to run this example. I'm going to run it on 4 threads. And we have the larger loop bound. It's like 3 to E8. It'll take just a minute. Okay, so here's the output from this Kokkos space-time stack tool. So here are the 3 kernels. So you can see that here we have a view initialization. So this is the Kokkos built-in view initialization that just runs by default. and then we have the two functors that we actually wrote in the code. And because we have a functor to already initialize the view, this default initialization is just pure overhead. The other thing you can look at is the memory. So you can see the max memory allocated. So if you're on MPI, this would just be for the high water mark on a single rank. You can see that we only have one view, A, and then this is the number of memory. And then we also can look at the system memory. Just note that on a Mac, this is actually wrong. It should be in bytes instead of kilobytes. Okay, so now we're gonna look at this example and try to get rid of this view initialization, which has got a lot of overhead. So the way to do this in Kokkos is by using this view alloc. So this is added to the label, or it encapsulates the label, and then you just pass in this Kokkos without initializing. So I'm going to add that here. Initializing and then the label. Okay, and so this should turn off this. So by default, all the views are initialized to 0. It's just so that they're safe to use. But like I said before, we're already initializing this view to these values here. And so we don't want it to be initialized as 0 and then to these views because it's just redundant. It's not necessary. So now I built it again and I'm going to profile it again and just see if we got rid of that overhead. You can see it ran faster and we only have 2 kernels now and we got rid of that initialization. Okay, so here's some gotchas that you need to keep in mind when using Kokkos. So virtual functions, they're typically not supported in parallel regions on GPUs unless you jump through some hoops. So I would recommend just avoiding them if possible. There's some more information here. But the problem is that when you have a virtual function, the V table is created on the host CPU and CPU memory. And you, like I said, you have to jump through hoops to get that V table on the device so that you can reference or dereference a virtual function call in the GPU. Now note that this is just inside like a parallel 4. You can definitely use virtual functions outside of parallel regions with Kokkos, but you just can't use them inside the parallel region. Another gotcha is using a view of view. So that's like saying I want a view and then the type is another view. That does work. The Kokkos developers actually heavily discourage that. You can see why. There's some information here. But I've actually found that this could be fairly useful if you need like a jagged array. So if you have, you could have a view, like the outer view, and the inner view is of different sizes. So this is kind of like using pointers and then having different allocations for the outer array. There are some gotchas. You have to deallocate in serial to prevent race conditions inside of profiling tools. But I use this in like Reacts FF, as well as for the custom data structures. And then the last gotcha is that you can't use data objects that allocate host memory on the GPU. So for example, standard vector allocates GPU memory. You try to use or reference or use standard vector on the GPU, then you're going to get a segmentation fault. There is a drop-in replacement Kokkos vector you can use instead. But again, just remember that any CPU memory is typically not accessible on the GPU. Okay, so a few additional Kokkos resources. So Kokkos has fairly good documentation. You can see their wiki. There are additional tutorials. So we've gone through a few tutorials, but there are many tutorials you can look at and work through on your own. There's the Kokkos lecture series, which is many hours of YouTube. It was created during COVID. And so, there's just hours of discussion and lectures on how to use Kokkos. The Kokkos Slack channel is very good. It's very active. So, if you just have a general question, you can go there and or if you have find a bug or just want to, have a discussion, that's a really good place. The Kokkos developers are very active there. There's also the Kokkos GitHub site, but it's discouraged to ask just questions. That's more for the Slack channel. But if you have like a formal bug report or a formal feature request, then you can certainly submit a ticket there. Or if you want, have some code to contribute, you can also submit a pull request on the Kokkos GitHub site. Let's see, this is my last slide. So I talked about this yesterday, but one last thing to be mindful of is to get good performance is processor and thread affinity. So you need to control how you're binding your tasks and threads to the nodes and cores. So you can use the MPI run or srun arguments like bind to core. If you're running on a supercomputer like Frontier, they often have scripts that will show, visually the affinity, just to make sure that you're not doing something silly, like binding all of your threads to the same core, which would give, horrible performance. They're all spread out, and just make sure you get what you're expecting. There's more OpenMP variables like OpenMP proc bind and OpenMP places, and then lastly, you just need to pay attention. For example, if you're on a dual socket system, then you just need to make sure that the MPI tasks driving the GPUs are on the same socket as the actual GPU, and that you're not trying to go across the socket, which can have overheads. Right, with that, I'll take any questions. Otherwise, I think we have a break.
Yes, we do. It's nothing on Slack, just a big thank you.
Okay, great.
Yeah, so, yeah, let's continue at 11.
Okay.
That would be something like that. Yes.
Oh, that's a new assumption.
Yeah.
That's a new assumption. Yes. There you go. Okay. All right, so we talked about, just kind of general Kokkos. Now we're going to talk about Kokkos and how it's used inside LAMMPS specifically. Okay, so I think everyone is familiar with LAMMPS, but it's open source molecular dynamics code. Focus on materials modeling, but can also do bio as well as mesoscale. It's more generally just a particle simulator at varying length and time scales. It uses domain decomposition for parallelism with MPI. You can do relaxation dynamics as well as non-equilibrium molecular dynamics. We're going to talk about GPU and OpenMP, and it can be coupled to other scales. So just a reminder, there's several different accelerator packages in LAMMPS. And so these complement the vanilla C++ version. And I'm not going to go into a lot of detail, but you might wonder, when should I use the GPU package versus the Kokkos package? Well, the main difference is the Kokkos package is trying to run everything on the device, whereas the GPU package only runs a few kernels, and then everything else runs on the host CPU. One nice thing about the GPU package is that it supports reduced precision. Kokkos package only supports double precision. Okay, so in the Kokkos package, and when I have a capital all caps Kokkos, that means Kokkos implementation in LAMMPS. So Kokkos, not all caps, is just like the Kokkos library, but Kokkos all caps is the Kokkos package. So there's many options that affect performance that we can set inside the Kokkos package. The documentation is here. So for example, we can set the Newton flag on and a half neighbor list. Often the default values are good, but not always. So sometimes it's faster to change the defaults. And I want to go through a few of these just because they're commonly seen inside the code. And so it will be helpful for you to understand what they mean. So in LAMMPS, we use a neighbor list. And they're just a list of interacting atoms inside a spherical cutoff. We also include an additional skin, which helps us to not have to build the neighbor list every time step. So here's this green atom is the central atom. Here's a cutoff, and then all the blue atoms are inside the neighbor list. For a full neighbor list, each pair is stored twice. So you can think, currently this green atom is a central atom and it interacts with this neighbor. But if you shift the perspective so that this is the green atom, then it's also going to interact with this neighbor. It gets stored twice, it doubles the computation. The nice thing about a full neighbor list, as I said before, is that it doesn't require atomic operations for thread safety. So it could be faster on GPUs for pairwise potentials. But if you try to do the same thing with a mini body potential, then you're not just doubling the computation, you could be tripling or more, and it may not be profitable. So instead of a full neighbor list, this is a half neighbor list, where each pair of interacting atoms is only stored once. This is usually better for CPUs, but it requires atomic operations for thread safety if you're running on a GPU or with multiple threads. That said, many newer GPUs have fast hardware atomics for double precision. And so this half list can be better, especially for mini body potentials. On NVIDIA GPUs, I think the last time I looked at this, it was about equal. A full neighbor list was still a little bit faster for Leonard Jones, but not that much faster than a half neighbor list. because of these incredibly fast hardware atomics on GPUs. So then there's also the Newton option. So if Newton is off, and it means that if two atoms are on different processors, then both processors will compute the interactions. It's like in the ghost region. And the force information is not communicated. If you turn it on, then you save computation but increase communication. In LAMMPS, you have to do what's called a reverse communication. And so for GPUs, Newton off is almost always better. For CPUs, Newton on is almost always better. But it does depend on how big your problem is, the cutoffs, and a few other, aspects of your hardware. Okay, so we talked about domain decomposition in LAMMPS. Well, this is how we parallelize with NPI. So each processor owns a part of the simulation box and all of the atoms inside this subdomain. So this is like processor 1, 2, 3, 4. So these are the different NPI ranks. With Kokkos, we're going to thread on top of these subdomains. So this is processor 1. So if I'm just going to zoom in on this first processor subdomain, then we're going to further parallelize on top of the NPI, and each thread is going to process a subset of the atoms inside the subdomain. So if we have two threads, then you could think of splitting up the loops over atoms. So each, the thread 1 is going to do the blue atoms, and thread 2 is going to do the red atoms. And again, these threads run concurrently, no guarantee of order. So in LAMMPS, we typically thread over owned atoms. That could be like atom in local, or also the neighbor list has the inum variable. We can additionally thread over neighbors to expose more parallelism, but that does have some overheads. If you run with a simple pairwise potential, then this is the default if you're running with 16,000 atoms or less. And so we expose more parallelism by threading over all the neighbors and not just the owned atoms. You can also use, threading over neighbors for expensive machine learning potentials. Typically, you only have, you have low atom counts per GPU. So you might, only have 1,000 atoms or a few thousand per snap. And so in Snap, we actually thread over 3 levels, which is supported by Kokkos. So we loop over atoms, we loop over neighbors, and then there's a bispectrum. You can also flatten multiple loops. So if you want to expose more parallelism, you can, flatten the loop into a single loop, and then just use a simple flat range policy in Kokkos. With Kokkos, we typically only use one NPI rank per GPU. You may think, well, my CPU has 36 cores or 110 cores. Why are we leaving so many CPU cores idle? Well, the reality is that if everything is already running on the GPU, then there's really nothing that the CPU can do, even if you have idle cores. And on modern supercomputers, a lot of the flops are on the GPUs anyway, so you really aren't leaving that many flops on the table. There's just really no good way to use all of the CPU cores if everything is running on the GPU. If everything is not running on the GPU, then just like in the GPU package, you can use multiple ranks per GPU to help parallelize the host calculations. It's important to remember to enable CUDA MPS, the multi-process service, if you're running on NVIDIA GPUs with more than one NPI rank per GPU. There are overheads, and so if you can port more things to Kokkos, then typically that is better than trying to run multiple NPI ranks per GPU. Jacqueline, do you have a question?
Is it still the case that with Kokkos, only one backend is supported for the same executable of LAMMPS?
Yeah. So you currently would need to build separate executables if you're gonna run on, different types of GPUs. Okay, so we talked about execution spaces in Kokkos, but now let's talk about them specifically in the LAMMPS context. So in LAMMPS, we have an abstraction. So LMP host type is the CPU backend, which could be serial or OpenMP. LMP device type is the GPU backend, so CUDA or HIP or SYCL. In LAMMPS, all the paracels are templated on device type. So this is a template parameter that can be either host or device. So if you see LMP host type, that's always host. If you see LMP device type, that's always GPU. But if it's just device type, this is a generic parameter that can be either host or device. The compiler, because we templated it on both of these two, it actually creates two versions of the Kokkos code in LAMMPS, one for the CPU backend and one for the GPU backend. And then users can choose at runtime which version to use using the LAMMPS suffix command. And so in this manner, you can instantiate in the LAMMPS input script. If you use the kk/host suffix, then it will run this style on the host. By default, it runs it on the device. And so in this way, you'll see a lot in the code. Most everything is templated on the device type, and this is why. It's so that users can choose to run on the host or the GPU. And there's also some cases where we can actually overlap host and GPU computation as well. So for this reason, we generally must not use this LMP device type directly, because this is hard coding GPU. We need to use this device type template parameter instead, because the user could be running on either host or GPU. And this here hard codes GPU, which is not what we want. Okay, so we talked about views in Kokkos. In LAMMPS, we have some more convenience abstractions or structs that contain many different kinds or types of views. This is in source Kokkos type.h. It contains nearly any type of view that you would ever need to use in LAMMPS. So like 1D arrays of integers, 2D arrays of integers, 3D arrays of doubles, all those are already included. And so in this struct, there's some namespaces. So again, we talked about this execution space. So we have this array types that has all these different types of views, and then we have these namespaces. So dat refers to device array types. So that's templated on the GPU execution space. Hat or host array types refers to the array types templated on the host execution space. And then we also have just an array type, which is templated on device type. And again, that may be either host or device. And this must be defined in each class or functor because it needs this template parameter, which depends on the class. It's specific to each class. And then further, if we have dat t dual underscore, and then this could be like int 1d. So any t dual, this dual is a dual view. And we'll talk a little bit more about this later. Anything that's just t underscore with no dual is just a device view, so a GPU, it's like the default execution space. And then hat is with the t underscore as a host view. So again, we should not use the dat t underscore because this is hard coding a GPU. We should use this array type instead. There are some rare exceptions, but it's usually in core code that you probably won't have to worry about. You can define new view types. So if you need like something exotic, like a 7D view or something, you can define that. There's an example here that we needed a custom view for EAM. So you can look at that example. Okay, and then there's some nomenclature of the view names in LAMMPS. So K underscore, so this could be like KX for positions, means it's a dual view. D means it's a device view. H underscore is a host view. And then sometimes you might see L underscore, and that means a local copy of a device view. So we use that for lambdas because there's some gotchas that we have to make a local copy. Any questions to this point? Okay, so we talked about allocating memory. So in LAMMPS, there are some memory, there's a memory class, and then there's like a create function and a grow and a destroy. And not all of the styles are ported to Kokkos. So sometimes we have to maintain compatibility with legacy data structures. So if you want to dump out positions in a dump file, we haven't ported the dump file code to Kokkos, and so that has to interface with Kokkos views. And the way that we do that is we actually alias the pointers of a dual view to the LAMMPS legacy data structure. So the host view in a dual view is actually it's the other way around. So the legacy view, like the X atom array pointer, is just pointing to the host view in this dual view. So it's aliased. It's done for all of the atom data already. All the positions, forces, velocities are all aliased. What this means is that it constrains the layout right for anything that's aliased, because C++ only supports layout right arrays. And so it may not give optimal performance. We've actually measured it, and it's not as bad as you would think. Unless you're using atom data, don't alias if you can get away with it. So if you don't alias, then you can use a more optimal layout, like layout left for GPUs. And then also we have another helper function, which is this mem kk realloc Kokkos. So let me just back up a little bit. So we alias using this memory Kokkos create Kokkos. So this takes both a dual view and then the legacy pointer, and it will just automatically alias. So you just and then you put in a label, and it will just take care of everything for you. If you don't want to alias, then you can use this realloc Kokkos instead. This also, we talked about avoiding initialization overhead by putting that Kokkos view alloc and to turn off initialization, so that does this automatically. It also will free, just call the empty constructor on the view first, and then reallocate the view, which avoids doubling your memory. Because with reference counting, if you don't free first, you'll have two copies, and then it will double the memory of that view. So this does it all under the hood. It's a nice helper function. If you, but the one thing to remember is that this realloc Kokkos does not preserve the existing values, so it's just going to clear all the memory and reallocate it. If you need to grow a view, then you can either just use view resize, which will preserve the values, or you can use this memory kk grow Kokkos, which is analogous to create Kokkos. And so this takes a dual view and the legacy pointer and will keep it aliased and preserve the values. Okay, so we talked a little bit about data transfer. So in LAMMPS, we use atom masks to control which views are transferred. So this is like the dual view sync and modify. So we have these masks, at, like X mask is positions, F mask is forces. We also have an all mask, which just would transfer or modify all of the atom arrays, and then an empty mask. So we should always use this atom Kokkos class, sync and modified, if possible. So if it's like an atom array, like positions or forces or velocities, then you want to use something like this. So it's atom KK sync, and then your execution space could be host or device. And then this is just a mask, so you use the bitwise or operator to say I want both positions and forces to be synced to, you know, the GPU. The reason we do this is because this has some, this is a wrapper that has some extra functionality. And so instead of, you know, using K_X sync, we use these flags with these atom masks instead. Notice that this is modified and not modify, because that was a clash with the modify class in LAMMPS. So just be aware of that. Also, all paracells define two variables, that's data mask read and data mask modify. There's only one parallel kernel in this in your code, then it's fine to set these data mask read and data mask modify and use that. This should be capitalized, but in atom KK sync, and then just put in data mask read. Otherwise, it's better to just define these two variables as empty mask and then actually set the atom masks directly instead. And that way you can customize for different parallel regions that need different kinds of data.
So Stan, as I understand it, the reason when you write proposed code for LAMMPS to make sure you set these masks carefully is for different input scripts, you don't know what's going to be where, and different things can be used, which may or may not be Kokkosized. And therefore, if these masks are correctly set, then the code itself will ensure that data is current on this GPU or the CPU, whatever styles you're using.
Yeah, exactly. So you're basically just telling it what data am I reading and what data am I modifying. And this is also how. So this is how we can run a non-Kokkos peristyle or fix in Kokkos. It just defaults to all mask, and it just transfers all of the data because we don't know what we need for this random, you know, style. And this is one reason why there's overhead, because the code will just say, I don't know what this is. I know it's not Kokkos. I'm just going to transfer all the data using all masks. So it's one reason why porting styles Kokkos gives a speed up, because then we can, you know, just say, well, actually, we only need the X and the F mask and only transfer that data.
So even if a peristyle is not Kokkosized, can it set these masks so that Kokkos doesn't pull everything down?
It can, and we do that in some cases, but generally, we haven't gone through all the peristyles. We just set, it just is default all mask, and then you can overwrite it. But yeah, that could be an optimization, but it would be also a lot of work. Okay. So again, if the LAMMPS style is not ported to Kokkos, it will just run on the CPU in serial. So you really have two overheads. The first overhead is that it's not parallelized, so it's just running in serial. The second overhead is that you have to transfer data every time it's invoked. And that's taking all the data from the GPU to the CPU, running it in serial, and then transferring. You don't know what you modify either, so then you have to transfer all the data back up to the GPU as well. So, you know, if you port something to Kokkos, it's almost guaranteed to improve performance by reducing these overheads. So in LAMMPS, we often use this dual view sync and modifying device and host to transfer data. Again, this is not for like the Atom KK data. This would be like for a local view inside your class that's not aliased. You can also use Kokkos deep copy. So we kind of use dual views and deep copy with create mirror view copy interchangeably. So either one is fine, but just remember that if it's something in Atom KK class, you need to use this Atom KK sync instead of just the dual view sync modifier or deep copy. Okay, if you've ever looked at LAMMPS Kokkos, you may have been confused by copy mode. So this is a flag that we set when we're using tags in a class, or if you're using this Kokkos class lambda, which does the same thing. It's when we pass this class, so star this as the functor, it actually creates a copy of the class. And then after the parallel region, that copy of the class goes out of scope. When it goes out of scope, the class destructors get called. So that includes the Kokkos class as well as the parent destructor. The parent destructor often has memory, like the per atom arrays. And so then it tries to deallocate this class memory prematurely. And that can lead to a segmentation fault or memory leaks or a host of issues. And so the way that we deal with this is we protect all the destructors with a statement if copy mode return, and then we set copy mode to 1 just before parallel region in Kokkos, and then set it to 0 at the end of a parallel region so that we don't leak memory. So, this is just a workaround to get around this class destructor being called. So if you get like weird memory issues or segmentation faults, then double check you did this copy mode thing correctly in LAMMPS. Okay, another thing that you'll see a lot in Kokkos as well as other accelerated packages is templating for performance. So templating parallel regions can reduce runtime overhead. So if you have like a if statement, then typically, that could be expensive inside the loop. But if it's a template parameter, then the compiler can create 2 branches of the code and then move the check to compile time instead of runtime. If you find that that's not the case, then there's an additional hammer from C++17, this if const expr, that you can basically just say, no, you will create 2 branches. And so this is the hammer that you can use to force the compiler. So in LAMMPS Kokkos, you can template functors, you can template tags, as you'll see. I don't think you can template lambdas yet, maybe with C++ 20 or later, but I'm not sure how to do that. But this is really a way to reduce runtime overhead. So like I said, if you have this if template param, then the compiler knows it's a compile time constant and it can optimize it at compile time. And this is also one reason why it takes longer to compile Kokkos. Template metaprogramming is really trading runtime overhead for compile time overhead. So that's why it takes a long time to compile Kokkos LAMMPS, or relatively long. Okay, so as far as initialization and setup, we typically assume that a user is going to run for a long time, like an hour or longer. And so it's typically not worth it to try to port initialization and setup kernels, like create atoms or things like that to use Kokkos. And, they probably won't run on the GPU well anyway. And so what we typically do is like I showed, you can create a host mirror, and then you'll, do all your initialization on the CPU, and then just copy that up once, and then you use that on the GPU. It's the same for CPU operations like load balancing. So we haven't ported, fixed balance RCB to Kokkos. It really wouldn't run well on the GPU. And so if it's really infrequent, like say 1,000 time steps, every 1,000 time steps, then it's just not worth it, and you don't really need to worry about that. It's the same for thermal output. So anytime you do thermal output, it doesn't know what data you're going to use. Are you going to dump all of the velocities in a dump file? And so it just transfers all of the data down to this from the GPU to the CPU, and that can have overhead. And so you want to keep thermal output to a minimum. So say again, only every 1,000 steps or less. Frequent is a heuristic, or maybe every second or less, or you just don't want to do it every time step. That can have significant overhead because you're transferring all this data every time step. Also similar for fixes that haven't been ported to Kokkos, like fix at Atom or something. And in that case, it's better to call it every time step, every 10 time steps than every step, which is reasonable normally because your time step is small and the simulation positions haven't really changed that much in a single time step. Okay, talking a little bit about polymorphism. Nearly all Kokkos package classes are derived from non-Kokkos parent classes using polymorphism. So that's like overriding virtual functions. So, there's a compute function in the parent class that gets overridden by the Kokkos class. So then that gets called instead of the parent. Go ahead.
Sorry, I had a question about the previous section that we just discussed. So, when you say every 10 or every 100 time steps is better, is because that the dump is on the CPU, is that right?
Yeah.
Why is it that you just don't port dump as well to GPU? Avoid this.
Yeah, so you really, in order to output the standard out or to a log file, the data really has to be on a CPU. That's really a CPU operation. So there's really just no way, even if we ported that, we'd still have to transfer the data at the very end to print it out into a file. Okay. Okay. So we're really trying to avoid code duplication. This is true of a lot of LAMMPS. We have a few core files, and then everything is derived from that, and it's just this hierarchy. But especially with Kokkos, like I said, we typically don't do initialization or setup code on the GPU, so it can just be copied from the parent style. And then with this polymorphism, we don't copy it, we just inherit it. And so it's just inherited from the parent and can be used by the Kokkos style. And so in this manner, we're only really overriding maybe the compute function and maybe a few others. And then another nice thing is that when we use the tags, and we're passing a full copy of the class to the GPU, any scalars in the class stack memory get copied to the GPU as well, and they can be used there. But if you have pointers, then those are pointing to CPU memory, and so those have to be changed to views. Another thing to keep in mind is that any scalar references the host memory, so like force, like if you have a constant like this Boltzmann constant, it has to be copied into a class variable because you're using a pointer, and this pointer is pointing in CPU memory. You just need to make a copy into the class, and then it will be copied up with this class in the device code in stack memory. As we said before, virtual inheritance and like multiple inheritance in device code is typically not supported just because of the two memory spaces, and the V table is in CPU memory and it just doesn't work. And so there are some cases where you have to duplicate code. So for example, in paired EAM, there's a few variants like EAM alloy, and we cannot use virtual multiple inheritance there with the device code. You can use it for CPU code. So like I said, all of the initialization and setup, that's all inherited, and and that all works fine. But if you're trying to run this on the GPU, then virtual inheritance does not work. And that's a GPU, that's the same with CUDA. This isn't like a Kokkos problem. It's just a problem like with CUDA or anything. It's just the two different memory spaces. Okay, a little bit about parallel reductions. So if you want to use multiple values, like all of the examples I showed was just a single scalar. If you want to use multiple values, then you need to create a custom struct with multiple members. So a good example is in Kokkos compute temp Kokkos. So we have actually 6 members here. You can take a look at that. There are some built-in Kokkos reducer types. So say, for example, you want to compute like the minimum or the maximum of the value instead of the sum. And so there's an easy way to do that with Kokkos. You can see this in the programming guide. You can also have very complex initialization and join functions for your custom reducer as well. And then one more limitation is that if you have templated tags in a class, it confuses Kokkos and you can only have a single reduction type. So if you need to have, one kernel do a reduction over integers and another kernel do a reduction over doubles, then you would have to use functors because each functor can have their own reduction type. But when you use tags, you put the reduction type in a class, and you only have one class, and so that's a limitation. Okay, I think I already talked about this previously, but just as a reminder, try to increase or expose more parallelism to saturate GPU threads to optimize GPU performance. Try to use the correct layout. Try to avoid moving the data. You can fuse kernels to reduce launch latency. Avoid allocating memory at every time step. So we try to over allocate views. And then watch out for view initialization overheads that we talked about. And then the last suggestion is to always profile to see what's actually important. So, if you speed up a kernel like 10x, but it's only, 1% of the runtime, then, that's not worth it. So just make sure that, try to look at what is the tallest, hole in the tent, and then work on that and then go from there. Okay, so here are some performance plots of real potentials in LAMMPS. So the green curve is an NVIDIA V100 GPU, and then the red curve is an Intel Skylake CPU with 36 cores. These are a little bit older, but it just kind of gives you a sense of the performance. So the y-axis is performance in atom steps per second, or million atom steps per second, so higher is better. And then this is on a single node or a single GPU, and this is increasing atom count. So you can see that you need, about 500,000 atoms to saturate a V100 if you're using Leonard Jones. The CPU is a lot more constant, but still, if you need maybe 32K atoms to saturate. But if you don't have enough work for the GPU, you're not going to get optimal performance. So in this case, ideal scaling is a straight line. For EAM, it's similar. For Reacts, we do a little bit better. Even at 1,000 atoms, the performance of the GPU and the CPU are about the same. There's a lot more work, and we've exposed more parallelism in Reacts, I believe. And then for Snap, this is a machine learning potential that's been optimized to death for NVIDIA GPUs. Some good work by Evan Weinberg at NVIDIA and others through the ECP project, the Execute project. You can see that we can scale down to very small atom counts and still maintain relatively good parallel efficiency. And this is because, like I said previously, we expose a lot more parallelism for snap. So we thread over atoms and neighbors and bispectrum, so 3 levels. And snap is very expensive. There's a lot of work. And so, that runs better on the GPU versus Leonard Jones is very cheap. And it's, basically how fast is your memory bandwidth here. Okay, so I have a few, a few instructions on porting Kokkos code in LAMMPS. So I'm gonna just go through these slides and then we're actually gonna do a demonstration. So how would you port a simple pairwise potential in LAMMPS to Kokkos? Well, there's actually some abstractions in Kokkos, pair.kokkos.h, which greatly simplify this process. So the first step would be to copy the header and the .cpp files from some existing style into source Kokkos. You're going to have to decide if you would rather copy some existing Kokkos pair style, or you want to copy the existing CPU, like the vanilla C++ style. Then you're going to, do some find replace on the old class name with the new. And then with this abstraction, you only need to change code in the energy and the force functions. And I'll show an example of this in a minute. You also have to make a few minor changes to the parent styles. So you may have to add a virtual keyword, or you also definitely have to add this copy mode into the parent destructor. Then you need to add the new styles that you've written into this install.sh script for the makefile build system, and then add the new styles to the documentation. So there's documentation for the pair style, but there's also lists of commands. So you also need to update like commands pair.rst. And so, if you do all of these things, then you should be ready to submit a pull request on GitHub. If you want to port a mini body or a machine learning potential or something that doesn't fit into this simple pairwise potential abstraction, then it's a little bit more complex. So again, start from an existing file, find replace, but then you're going to have to port loops over atoms to use Kokkos parallel for and parallel reduce. If you have a simple pairwise potential, this abstraction takes care of all of that. With the mini body potential, you'll have to do it yourself. It's not that bad. Well, I guess that's kind of relative, but we can talk more about that. You're also going to have to port arrays to use Kokkos views. So anywhere where you have, like an atom X for positions or F for forces, those are going to have to use Kokkos views. You still make a few minor changes to the parent styles. You still need to update the install script and still need to update the documentation. If you want to add a new Kokkos package option, then you would go to source kokkos.h and add a new class variable. You initialize it to some default value in the .cpp file, and then you'd copy and add a new parsing line that sets the value of the variable based on, some command name. And one thing to point out is that in command names, we prefer a slash instead of underscores. So, for example, if you wanted to set an atom map, then we use atom/map and not atom_map. So that's like the actual command that the user is going to type into the input script. We can definitely use underscores in the code, but for anything that's user facing, we prefer a slash. And then you just update the documentation in the package.rst file. Okay, so now we're going to look at some code examples. So first, we're going to example a simple compute, as compute add sphere atom KK. And then we're gonna port a simple pairwise potential, so that's peristyle soft. And then we're gonna look at the EAM mini body potential. Okay, so I'm in LAMMPS, so I've cloned the LAMMPS repository. I'm in the source directory. I'm gonna look at a simple compute, which is compute av sphere atom. So this is a compute that I wrote. It's pretty simple. It just basically takes an atom, it looks at all of the neighbors in a spherical cutoff and computes a couple different properties like the potential energy and the density. No, I think it's the density and the temperature. And then you can use that as a local temperature and a local density, and then you can use that for like visualization in Ovito. So here's the header file in LAMMPS. So this is the CPP file. This is just the parent style, not Kokkos. So you can see that this is the actual command name that the user types, which is alias to the class. And then we have the include guard, some includes, and then here's the actual class. So there's just a few functions, and this compute per atom is where the loop over atom is actually done. And this is what we're gonna port to Kokkos, or have already ported to Kokkos. It also does some forward communication on velocities. Just has a few variables. So like I said before, all of these scalars will be copied up with the class, but this array, like any pointers, this will have to be made a Kokkos view. If we look at the .cpp file, you can see what it's actually doing. So this is a constructor. It's just parsing some arguments, setting some default values or other values of the scalars. The destructor, so you can see that we have this copy mode in the parent destructor. That's important. That's just something that you have to add for every Kokkos style. We get a neighbor list, set some cutoffs. And then here's where the actual work is done. So we define some variables. We allocate some memory. So this result, if it's larger than the number of atoms or the number of atoms with some extra, then we're going to destroy it and recreate it so that it's big enough. We do some communication we need the velocities of ghost atoms. We build the neighbor list, and then here's the loop over atoms. So we just get some local variables to the neighbor list. We get some local variables for the atom arrays. We need the positions, the velocities, masses, type, and mass. And then we also have some, temporaries for a few constants. So here's a loop over owned atoms. So this is atom I, the central atom. And then we do some work to get, so we get the momentum of atom I, and now here's the loop over neighbors, so atom J. And then again, we're just, computing the distance, we're just checking if it's inside the cutoff. And then we're summing up some properties. And then after we do that, we can get the density for all the atoms inside the sphere. So that's just related to the total mass and the volume of the sphere. And we also get the temperature, which is related to the kinetic energy and the number of atoms inside the sphere. And then we store the density and the temperature for atom I inside this result vector. So it has two entries, and then we have, so that's the end of the loop over atoms and neighbors. And then this is a function for communication, so we're just packing a buffer of the velocities and then unpacking them. And then we have function to calculate the memory usage. Okay, so that's just kind of a tour of this C++ code. So what does the Kokkos code look like? Okay, so here we have the header file of the Kokkos version. And you can see that we have a few different templates. So we templated the class. So the default is this LMP device type, which again, that's the GPU execution space. And then same for if you explicitly list the /device suffix, and then we have the host as well. So this is where a user can either choose, I want to run the GPU or the CPU. This is how that's accomplished. So we inherit from the parent C++ version. And then you can see here, or we include that file, and this is where we inherit from the C++ version. And then we define a few type defs, so device type and array types for the views. And then this is the Kokkos version, and you can see that we only have two functions. We have a init and compute per atom, and init is almost empty because we're just calling the parent version, and then we do a few things to change the neighbor list. So really, we only had to override compute per atom, and everything else is inherited from the parent class, and we don't have to even mess with that. We're using tags. So here the tag is compute sphere atom, and then we have an operator for the tag, just like we showed with the Kokkos previously. We have to make a few of these constants class variables, and then they'll get copied up to the GPU. And then we have views for the atom arrays. So X, positions, velocities, mass, and type, and mask. We have some views for the neighbors, the neighbor list, and then we have a view for this result. So we have so if you remember, this T dual is a dual view with K underscore result. So this is a dual view, and then we have a device view as well that will just point to the device copy in this dual view. We look at the CPP file. You can see that instead of memory, we're including memory Kokkos, same for neighbor and atom Kokkos. So we're just, including some of the Kokkos versions instead of the regular versions. The constructor is relatively empty. This is a flag that says on the Kokkos style, we set an execution space from this device type parameter. So you can see that this class is templated on device type. So that is just, again, we go down to the bottom. We're templating this on both device type and host type, which just says basically user can choose to run on the GPU or the CPU. We're making two copies. Okay, and then we have in the destructor, we have this if copy mode return because we don't want to destroy the view until the very end. When it goes out of scope, we just, so that has to be set. And then in the init function, we're just calling the parent init, but then we adjust a few settings for the neighbor list to get a Kokkos version. And so that's basically exactly the same as the parent, except this addition. And then we have the compute per atom. So this is where we're doing the actual work. We're allocating some memory. So again, instead of just the result, so we're aliasing this result pointer to this dual view. So we destroy it and then recreate it as an alias pointer because this result is used in like other fixes. And so it has to be aliased. And then we also set the device view to the view of the dual view, whatever execution space we're running on. And so this is just allocating that 2D array that we're going to store the results in. We're doing communication on the host, so we have to sync the velocities to the host, and then we do this communication, and then we modify velocities on the host. This could be ported to Kokkos to get rid of this data transfer, which could, maybe give a little bit of speed up.
Why is it setting the flag that they're modified?
Because
Oh, just because we did the same. We're not modifying the velocities in this method.
no, it gets modified in forward com because when we sync it so that it's up to date on the host, and then the forward com is, putting the values on the ghost atom, so it's actually changing values in this array, and that's how we have to mark it as modified. We're actually touching values inside the velocity array.
But you don't. But it's not reading anything that would change anything about what the GPU does. The GPU velocities.
So we're going to use the GPU velocities later. So this forward com for computes I don't think it's ported to Kokkos yet. So it's just running it's just falling back to the host CPU version. I guess maybe I'm not understanding your question, Steve.
I'm saying this compute is using velocities to compute the temperature, but it's not changing the velocities of anything. So is this code is going to force stuff to be pushed back to the GPU?
Yeah, yeah, I see what you're saying. Yeah, so here later on, so we're going to sync all of the positions, velocities, mass, type, and mask to whatever execution space we're running in. Because we're going to use this, just assume this is a GPU execution space, we're going to use this on the GPU later. So when we do the forward com, it got modified on the host, and so we have to mark it as modified.
All right, I'll follow up with you on that. I'm still a bit confused, but okay.
We build the neighbor list and set some, local variables. And then we have to sync the data. Any data that we're going to use has to be synced. We set we set copies of the right view, whether it be host or device, because this dual view is templated on device type, so that will give us either a host or a device view, a CPU or a GPU view, depending on which execution space we're running in. So we get copies of this. We make copies of these constants so that they're in class stack memory. We have to initialize this result to 0. So you can just deep copy in a scalar value, and that will just set all of the values to 0. We set copy mode equals 1. So this is really important because we're gonna do a parallel region, which we pass in a copy of this entire class. When that goes out of scope at the end of the parallel region, it will call the destructor. But because copy mode is set to 1 and we protected all the destructors with this statement, it will just be a no-op, and we won't get this memory deallocation that we don't want. Here we're setting, this is just like a ranged policy. It's just a flat parallelism. We put in the device type as the execution space and the tag, and then we set the loop bound. So this is just 0 to inum. Inum is this from the neighbor list. So it's normally equal to the in local, like atom in local, unless you have a pair hybrid, and then it can be different. And then we do parallel 4. And then we unset copy mode so that it's 0, so that, you know, at the very end, we do want to deallocate the memory. We don't want to have a memory leak. And then we have to mark this result view as modified. And then we sync it to the host because that could be used by other fixes, like fix out Atom. We just don't know where it'll be used, so we have to sync it to host. Okay,
So that step there, that last step, we have this local result thing. But it really needs, array Atom needs to point to it so that other things in LAMMPS can get those results. Does that last line accomplish that?
so that last line just takes the data from the GPU and puts it on the CPU. Where we aliased it is here when we created it. This create Kokkos takes this dual view and the host pointer, and it just basically allocated the dual view and then took that pointer and pointed it to the host memory of the dual view. So here is where it's actually aliased.
Okay, and then array Atom is set to that. So now array Atom is pointing at what got pulled back to those.
Yeah, exactly.
Got it. That's what clearly in my mind needs to happen.
Yeah. Okay, and then we also have this operator, which is, this is like one iteration of the loop, like we showed in all those examples, along with a tag that says, you know, which one it is. In this case, we only have one tag, but in other cases, we could have multiple tags. And so here we're doing really the same thing. We have, this is for Atom I. We get the neighbor list and get the indice. We store some positions. We compute the contribution from Atom I, and then we do a loop over neighbors for Atom J. But you can see here, this is referencing the view. So again, we use the parentheses because it's more than 1D. Instead of, you know, the bracket, right? So the CPU code would just have like this, right? But with Kokkos views, we have to use parentheses and commas. And then same loops, except we're using views. And then, you know, this is the same, basically the same work. And then we get down here, we have our density for this, you know, this local density of around a specific atom and a spherical cutoff, and also the temperature. And then we have to store the result in this view. And then again, that view, so that's on the GPU stored here. And then after the parallel region, we say we modified it on whatever device type we were running on, and then we have to sync it to host so that we can use it in like a dump file or whatever fix that's now ported to Kokkos. And then the very last part is just templating. It's just instantiating the templates for device type, and then if you're running on a GPU, you also have a host type. So any questions on this compute? Okay,
Sorry,
yeah,
can
go
you
ahead.
please go to the top of that block where we have this compute?
Was it the very top or?
You just a compute,
Oh, the compute per atom.
yeah, okay. So this is not the functor, right?
No,
The functor is the,
yeah. So this calls the functor. So the functor is actually like the whole class, but then we have this operator here that has a tag, and this is what's actually called for one loop iteration.
right,
Yeah.
right, okay, yeah.
So this Kokkos parallel 4 with this tag, we'll call this operator.
Right, okay.
Okay. All right. right, so the second example is to port a simple pairwise potential. So this will use that abstraction that we talked about. You know, it's not as complex as doing everything from scratch. Okay, so we're gonna start with pair soft. So pair soft is basically like sort of like a cosine functional form. It's just you have like really overlapped atoms, and you try to use a normal pair cell, they'll like explode, and then it will crash your simulation. So pair soft is a really gentle pair style that will just allow them to overlap or like unoverlap, push apart without blowing up and crashing wax. So we just look at the C++ code, the parent class, it's fairly standard. You know, if you compare this to Leonard Jones, it's pretty similar. The work is done in compute. And then you have a few other functions, like all the write, restart, read, restart, all of that is CPU code, and all of that will just be inherited by the Kokkos class, and we won't have to touch that in any way. We really just have to override this compute function and then a few other things as well. It's just got a couple parameters, prefactor and cut, and then an allocate function. So if we look at this, the .cpp file, constructors basically empty. Destructor doesn't have copy mode. We got to add that. And then compute is, so here is the loop over atoms. So we're gonna, we read positions, forces, and types. Here's the neighbor list, and then here's the loop over atoms. And then the loop over neighbors. We just check it and see if the distance is inside the cutoff. And then this is the force computation. So it's taking the distance, and so it's pi times distance divided by cutoff, and then that's for forces. Or maybe let's just look at the energy. I think it's simpler. For energy, it's just this prefactor. So that's like A times 1 plus cosine of X, or you know, some arg, and arg is just pi r divided by cut. Maybe I'll just show this. Doc page real quick. So it's just here. This is the prefactor 1 plus cosine pi r cut. And then the forces are just a derivative of that. But you see in here, you know, you have like Newton flag. With Kokkos, it's even more complex because you have a half neighbor list and a full neighbor list. But all of that is abstracted away. And so we don't even have to think about that. Same with this EV tally. And then the other functions, you have an allocate function, which is just allocating some memory. You know, this memory create, prefactor and cut, some settings, coefficients, initialization, and then all this restart stuff we don't have to worry about because it's all on the host. And the same with the single function. That's not a thing in Kokkos because Kokkos is doing loops over atoms, and this would not be efficient on it. Okay, so just one other thing we need to do. I know that we're gonna override this allocate function, so we need to make this virtual because Kokkos is gonna override this. And so we just have to make these two simple changes to the parent class. So we added the copy mode into the destructor, and then we're making this virtual. And that's really the only thing we have to change in the parent class. If this was private, then we also have to change it to protected so that it could access this cut global. Okay, so now we're gonna copy this and make a Kokkos style. And for this case, I'm going to start, I'm gonna go to Kokkos. I'm gonna copy a pair LJ cut Kokkos and copy that into pair soft Kokkos. And same for the .cpp file. And the reason that I'm starting with the Kokkos version is because it has all the boilerplate and everything that I need, and it's going to be a lot easier if I just start with this existing file. And I'm going to start working on the header file. So first, I'm just going to do some copy paste, LJ cut to soft, and here, LJ cut to soft. And then same with the header guard. Okay, and then I want to inherit from the soft header. And that's the bulk of the changes for the header file. The only other thing we need to change are the coefficients. And so we don't have all these Leonard-Jones parameters. We just have prefactor. And then we have a cut. And to be honest, you don't have to understand all of the abstractions in this class to, make a new class. I mean, we can go through it a little, just really quickly. So, this is defining some type defs. This is the compute function. And then this params LJ is just a struct that I'm going to call params soft. This is just the struct of params. And we'll talk a little bit more about that. It has some views for like atom, X positions, types, forces. It has some parameter arrays, but you can just think of a lot of this as boilerplate that you just need to copy over. And then a lot of this is like just how it interfaces with Kokkos, the abstraction layer.
So you just said that that's the parameters for the soft potential.
Yeah.
But then you also said that it includes views for the positions and forces in there. Is it both the parameters class or? Is it
So the params is just like Leonard-Jones, sigma and epsilon.
Okay.
Yeah, or in this case, the prefactor and the cut that we need here. I'm just gonna finish this. And here. Okay. So that's the params. And we're gonna go to the .cpp file. We're gonna do like a similar copy replace of LJ cut with soft. Change the include file. Okay, and then this again is like saying on the Kokkos style. This is that data mask read and modify. Because we only have one kernel, we can just set it here. So we're gonna read the positions, the forces, the types. This energy and variable is a no op that I need to get rid of. And then we are gonna modify the forces. The destructor already has copy mode. And then here's the compute function. So this is where the actual work is done. And again, you can just think of a lot of this as like boilerplate. We're allocating some per atom arrays. Okay, and then here's where we're actually syncing the data. So again, I set it in above in data mask read. So read was XF type. And then we're syncing some of these internal class views. And then we modified the data mask modify, which was just F. And again, this thing needs to be cleaned up a little bit. And then here's where we're actually setting the views based on device types. We're taking a dual view, we're setting a device view, making a few more local copies. Again, like this force special, this won't work because it's a pointer to CPU memory. So we have to copy that into a class variable, which gets copied up to the device. We set copy mode equals 1. And then this is that abstraction where we just call this pair compute. And we put in the neighbor list as well as a pointer to the class here. And then we have to accumulate the energy, the virial, and the per atom energy and virial. And then we set copy mode to 0. So again, this pair compute, this is an abstraction that, like, normally we'd have to call a Kokkos parallel 4 or a parallel reduce, but this takes care of all of that, so it's a lot simpler. And then we just have 2 kernels that we need to override. So this is the forces and the energy. Okay, and so we're gonna, let's see. And then this is allocating memory. Again, you can think of this as boilerplate. So really the only things that we need to change are parameters. So we no longer have these Leonard-Jones parameters. We have prefactor and cut. Get rid of these. And cut squared is a little bit different. That's in all the peristyles that's used to compute or for the distance calculations. So that's why it's a separate view. Okay, so we did the parameters. And now we just need to change the energy and the force. So if we go back to the parent style, we can look at the functional form. So it's right here. So here's the energy. So I'm gonna take this and copy up here. Okay, and we don't want the forces, but we do want R. Right now I'm working on energy. Okay. So, and in Kokkos, you'll see this F float. That's kind of left over from trying to add reduced precision. You can use that or you can use double. I'm planning to change that, so it doesn't matter. But F float is like a force float, just as a double. Okay, so now we're just gonna return factor LJ times. So this stack params, is maybe a little bit confusing, but it's just like either using stack memory, which can be faster, or if you have too many types, then it falls back to global memory. And so that's why there's this conditional on stack params. I'm gonna take this, I'm gonna make another variable. Okay, and then we get rid of this. I'm just changing it from the Leonard-Jones functional form to the soft cosine. And then I also need prefactor or factor I LJ, which I can get from here. Okay, so look right. We've got arg, which is my pi. We've got r. Oh, we need to do cut as well here. Okay, so we have my pi, r, cut, prefactor. So that is basically the energy function. The force function would be similar. We just take the derivative from the parent style, copy that in, do the same thing. Any questions on this?
I had one question back up where there was a sync of the params.
Mhm.
Is that every time step making sure that the current values in prefactor are pushed to the GPU?
Yeah,
Okay.
in theory, if we knew that it's never gonna change after we initialize it, then we could just move this into initialization, but it doesn't hurt anything.
Well, actually, for soft, it is typically driven by fixed.
Oh, yeah.
So that the prefactors are changing every step to make the potential go from super soft to harder to push things apart.
Yeah,
So that's why I wondered if that was getting the sync
uh-huh,
to the GPU.
yeah,
So it sounds like that is, okay.
yeah, uh-huh.
And what related to that, if the parameters don't change between time steps, does that sync become a null?
Yeah, it's just a no op because we haven't modified. So if we go down here, this is where we actually modify the params on the host. We only do that when this init1 is called. And so it will only sync it once, and then because it's not modified, it's just a no op.
Wait, but fix adapt is gonna use that extract function thing, and it's gonna overwrite values in the prefactor.
Okay.
Does this know that, so that it will sync it to the GPU?
Apparently not. Yeah, so
Okay.
so then you have a bug because you're missing a modify. So that's something we should look into.
It'd actually be the same for Leonard Jones. People run, time varying sigmas, time varying epsilons.
Yeah.
With Leonard Jones to do kinds of thermodynamic stuff. So that's another thing that those would have to be pushed to the GPU.
But fix adapt runs another function to update the pre-computed factors.
Does it call init1 or something?
No,
No.
yes. it has the pointer that it overwrites, in this case, prefactors directly, because it has that one,
So you're saying it calls extract,
get the pointer.
get the pointer. So we should add, we should override extract and then modify the params in that one on the host.
Well, actually, it only gets the pointers once because it knows that that's never gonna change.
Oh.
So what I'm saying is fix adapt is triggering changes in parameters for several pair styles.
Uh-huh.
But soft is one that's almost always used that.
Yeah, so that's bad. We should look at. Okay. Okay, so I'm not gonna go into the rest of the forces, but I do have a copy that I've already done. Just so you can see, so those. So here's the forces. It's very similar. You know, we have the same vector LJ, cut, prefactor, and then it's just a different map here. So it uses a sign, which is the derivative of the energy with the chain rule. And I did verify that this compiles. One other thing I had to do was add, for to use MyPy, I had to use this map const and include this header, which defines a bunch of map constants, which gives me the pi constant. Okay, the last.
So I was just checking, so fix adapt calls pair reinit, and pair reinit calls init1.
Okay, so then we'd be good. Because that would mark it as modified on host.
Now it has to, because init1 computes those pre-computed Lennard-Jones terms.
Yeah.
If you just change epsilon and sigma, you don't change LJ 1, 2, 3, 4, and then it has no effect in the force computation.
But for soft, prefactors direct, that still happens for soft too.
Yeah, this is in the base pair class.
Okay, the last code example, want to look at a mini body potential style. So this pairwise style, like if you have any pairwise, you can use this abstraction in Kokkos.h. You don't have to mess around with loops or parallel fours. You just have to change the functional form of the potential, which is nice. If you want to do a mini body, then it's a little bit more involved. We're going to look at pair EAM. So again, you know, same initialization of the styles or like linking them to the classes. You can just think of this as boilerplate if you want. We have multiple tags here. So tags for pack forward com, unpack forward com, initialize. We've actually templated some tags on the type of neighbor list, like half or full, and also Newton pair. And again, these templates are so that we can reduce the overhead of the conditionals of like the if statements inside the loop. Similar for E flags, that's like if you have to compute an energy or a variable. And so we have, you know, many tags. EM has many kernels, and each kernel has a tag. Here's the class. We template on device type, set some type defs. But we only have a few functions that we override, just compute and init style. And then each tag has an operator, can be either a parallel for or a parallel reduce. You can see here, here's a reduction type. This includes the EV float is like energy and the 6 variable terms as scalars. So many functions, and then here are the views. And then one additional thing we have here are scatter views. So with the simple peristyles, that's all under the hood. But here we have a bunch of scatter views. You can again think of this as like boilerplate. You just copy some more views. So these views are local to the class style.
Is this for data computed in the peristyle?
This is for the
Intermediate.
spline tables.
Also, this is for the potential parameters.
Yeah, this is the spline tables. The row is for what's computed in the peristyle. Well, it's like a temporary. Here is a custom Kokkos view. So we have a 3D view, but the last dimension is 7. So this is for spline tables. So this is the example I referenced of how to make your own view. So we typed up it, and then we get the device and the host versions as more typed ups, and then we can set these types in the class. We have a few functions for the splines to interpolate and read the files. And then we have neighbor lists and more views, and then that's it. And then we inherit this from Kokkos.h, the dev.r. Okay, so here's the .cpp file. In Kokkos, we don't support RESPA. We don't support single functions, so those are set to 0. This is a Kokkos style. We set these data masks, read and modify. So we're reading positions, forces, types, and we're modifying forces, which is exactly the same as Pairsoft. We have this copy mode in the destructor. But it's really the same as Pairsoft, except instead of having that pair compute, we have we launched the kernels ourselves. So we have these explicit parallel 4s with tags, and then we also have parallel reduce here. So for computing the energy, we have a parallel reduce. If not, then we just have a parallel 4 because parallel reduce has some overhead, and we don't want that if we don't need it. So this is like where we're templating. Here you can see like we're templating the tags to reduce the overhead. So if it's like a half neighbor list or a full neighbor list, and then we do some communication. We can launch more kernels, so it's fairly complex. But this is really just because we're templating. We have all these if conditions outside the loop, so that we can get rid of the overhead inside the loop. This is contribute is for a scatter view, and then finally we're summing up the energies, the virials, and the paradigm energies and virials. And then we free some memory by calling the constructor.
So I didn't see a forward communication, which is in the C version. Is that because of this NA app? Or NA full or?
It's there.
Newton honor.
So
There it is.
yeah, so we do a forward communication if we are using a full list. Or is that true, or maybe it's for both? I think we only do a reverse if we're using a half list.
Yeah, you always need the full forward
Yeah.
because you need to copy the computed data to the ghost atoms. And the reverse you only need for the half neighborless.
Yeah, Newton pair, and half neighbor list. Yeah, so we always do the forward. And then, okay, and then you can see that just like in the compute, well, first of all, so here's where we're reading the spline tables. We're just copying these into the host part of the dual view. And then we, do the sync modify to get it up to the device. So that's all just kind of on the host, same with all the interpolation and everything. This only done once at the beginning. And then finally, show you some of these operators. So here, like just in the simple compute, we have to actually have an operator, we have to have loops over atoms and neighbors. So here, so this is for atom I, and then we have a loop over neighbors for atom J. For computing things, we have to use here the scatter view takes care of the thread safety. So that's like the atomics. So we get, so A underscore is atomics, like a atomic thread safe. And then we actually use this because this isn't thread safe, computing this density because you're modifying both I and J. And with a half neighbor list, J could be the same as I, and so this has to be atomic. So that's thread safety. So if you don't have a simple peristyle, the things that you need to add are really this loop over atoms and neighbors. And then you also have to pay attention to like a half neighbor list and Newton on. But some of that will be inside the original CPU peristyle. You can just copy the same logic. Okay, any questions on EAM, Kokkos? All right. So we've gone through all the code examples. So if you're trying to port like super advanced features, so this could be like a new Atom style or styles with really complicated forward communication or like core features that aren't ported yet. My advice would be copy the closest existing Kokkos file and, talk to me on Slack or send an email. So we have a LAMMPS developer Slack channel, just lamps.slack.com, or our emails are listed here, or you may already have them from the workshop. But, if you don't have a good example, it can be hard. And so, feel free to contact me and we can discuss.
Yeah, so the developer Slack is invitation only. So you have to send an email to either me or developers@lamps.org to get an invite.
Yes. Okay, and a few more resources. So if you want to learn more about the Kokkos package and lamps, it's described here, speed Kokkos. There's also the Mat site lamps forum. So you can join and post new questions. If you want to just talk about how to use Kokkos, that's a great place. There's also GitHub. So you can submit a bug report. So like if you're running Kokkos and it's crashing or something doesn't seem right, you get a segmentation fault, then feel free to submit a bug report on GitHub. If you have some code that you're working on, but maybe it's not working or you can't compile it or something, feel free to submit a draft pull request on GitHub. And then, I can take a look or other developers and we can give you some suggestions. It doesn't, you don't have to wait till everything's like perfect to submit a pull request. You can submit a draft pull request and then it can be a collaborative effort. There's also the LAMMPS reference paper. So it, just kind of gives an overview of a theory of LAMPS, parallel algorithms, design features. It has some performance plots. So it's a good reference. That's all I have. Thank you. Yeah, and feel free to talk to me about programming too. I mean, that's the purpose of the workshop. So after the lectures.
I was kind of wondering, like, I think I know the answer to this question, but like, how does ghost communication affect the process? Because like Reacts FF uses QEQ, and so you have to transfer charges. But when I saw Reacts FF actually works better than most other potentials in the sense that you get a faster increase at lower number of atoms. So I guess it doesn't really matter that much.
Well, so maybe I don't understand the question. Like,
I understand, okay, because I'm trying to think of like how the communication happens, because I imagine like if you're using a bunch of GPUs, you have to like go from device to host, and then to host, then to device, I guess. Or, like,
Yeah. Yeah, so again,